Before 2017, sequence modeling relied on a specific architecture, recurrent neural networks, including LSTMs. If you needed a machine to understand language, recurrence was the strict default. But recurrence carries a mathematical limitation. To calculate the hidden state of any given step in a sequence, let's call it step t, the model must first finish computing step t-1. The process is inherently sequential. This strict sequence means the calculations cannot be distributed across multiple processors simultaneously. The dependency on the previous step acts as a hard physical cap on how large these models can scale. The 2017 paper, Attention is All You Need, proposed a total rejection of that requirement. The authors explicitly outline in the abstract that their new architecture, the transformer, dispenses with recurrence and convolutions entirely. This table reveals the structural difference in the network layers. Recurrent layers demand big O of n sequential operations, scaling linearly with sequence length. Self-attention drops that to a constant big O of 1. Reducing sequential complexity to a constant allows computation to be distributed across hardware at scale. This mechanism is why modern models can process trillions of tokens in a single training run. Processing every token simultaneously creates an immediate paradox. If the model ingests an entire sentence at once in parallel, it lacks a built-in mechanism to recognize the order of the words. This diagram outlines the solution. Raw data inputs are mapped into continuous mathematical representations known as input embeddings. To solve the paradox, the authors introduce a positional encoding. Notice the addition symbol. The model physically adds this encoding directly to the input embedding itself. The math driving this relies on sine and cosine functions of different frequencies. Every position in the text is assigned a unique oscillating value based on a geometric progression. Because the wavelengths vary across dimensions, the model can calculate how far apart any two words are by relative position, despite reading them both at the exact same moment. Conclusively, adding a fixed frequency vector to a word vector grants the system an absolute understanding of sequence. It entirely replaces the need for a recurrent loop. With the sequence hard-coded directly into the data, the embeddings move into the core engine of the architecture, attention. Scaled dot product attention packs input into Q, K, and V matrices. The dot product of queries and keys calculates token alignment. This is divided by a scaling factor to prevent stalled training. Softmax normalizes these into weights, which multiply against values. This sequence of operations allows every token to calculate its relevance to every other token instantly, processing vast dependencies without moving chronologically. Running a single attention function limits the model. It averages out the information, which restricts the network from focusing on multiple different linguistic dependencies at once. The authors bypass this by expanding the architecture into multi-head attention, detailed in the right-hand diagram. Instead of executing one broad function, the queries, keys, and values are linearly projected 8 separate times with different learned weights, running through 8 parallel attention layers, or heads. This forces the model to jointly attend to different representation subspaces. One head maps grammatical structure, while another isolates semantic meaning simultaneously. Zooming out, we track how these parallel heads integrate into the full encoder stack. Notice the add and norm steps. These employ residual connections and layer normalization, ensuring the network doesn't lose the original input signal as data pushes forward. The singular purpose of this encoder is to transform raw word embeddings into contextualized representations through massively parallel self-attention. That encoded data then passes to the right side of the architecture, the decoder, where the model predicts the sequence's next token. While the decoder mirrors the encoder structurally, it requires a specific modification to prevent it from seeing the words it is supposed to predict. Text generation relies on autoregressive properties. A prediction at position I can only rely on known outputs that occur at positions less than I. The architecture enforces this rule right at the base of the decoder, using masked multi-head attention. It implements this by blocking illegal future connections, setting those connections to negative infinity just before the softmax step. This strictly yields a zero probability for any future tokens. This masking mechanism ensures the architecture respects the sequence's temporal order during text generation without sacrificing its structural parallelism. The advantages of parallel attention delivered immediate results. This table logs performance on the WMT 2014 translation tasks. The transformer, BIG, established a state-of-the-art BLEU score of 28.4, clearing benchmarks set by complex ensemble systems. Looking at the training cost, it achieved these results in 3.5 days on 8 GPUs. That's a fraction of the computational expenditure demanded by the older sequential networks. By proving deep dependencies could be resolved exclusively through mathematical attention, researchers removed the primary bottleneck throttling deep learning for years. Model scale was no longer restricted by sequence design. The only remaining limitation was the total volume of available compute. The transformer's constant sequential complexity provides the physical architecture for scaling model depth and data volume, serving as the foundation for modern generative systems.